Hello there, and then welcome to a brand new video. We are still on the vector series, and in this lesson we are looking at resultant vectors. And I do hope you've gone through the other lessons and you've understood, because this is just a build-up of all we've been doing. So without much I say, let's quickly look into it. A resultant vector is a single vector that has the same effect as the combination of two or more vectors. You see? And it shows the total movement from the starting point to the ending point. What do we mean by this? So let's say this is a town A, and then I moved from town A to town B. You see, and from town B, I also moved to town C. Now, if another individual chooses to move straight from town A to C, we are still at the same destination. You see, so that is all resultant vectors is saying. So it is trying to say that if you move from A to B and then from B to C, you see, it is the same as moving directly from A to C. Exactly. Then you can apply it also in parallelograms as well. You see, so we are trying to move from A to C. Per our diagram here, someone chose to move from A to B. So from A to B, and then from B to C. So from B to C. You're going to say it's the same as moving directly from A to C. Or in other words, if you wanted to use this path over here, then moving from A to D plus moving from D to C. So D to C is the same as moving from A directly towards C. Now, before we proceed, take note of the following. So you need to be able to perform your vector addition, where we say that if you want to add vector A, B to a vector B, C, then since the ending here is the same as the beginning here, then it is straight away going to be what? AC. You see, so this is just a recap that will help us solve questions in relation to what? Resultant vectors. But then if you are to add A, B to vector C, B, you would have to do a rearrangement. The rearrangement here meaning that since this ends in B and then this ends, it begins with C, we can't do that. But rather, we have to write CB, CB, so that it will look like BC, such that the ending here will be the same as the beginning here. And this brings to mind what? Negative or inverse of a vector. So the CB here is actually equal to the negation of BC. You get it? So moving from C to B is the same as the negation of moving from what? B to C. Hence, instead of CB, we are going to do a substitution so that we are going to get AB plus CB, rather being what? Our AB. Then this here is the minus BC. So minus BC. You see? And with that now, since this ends and then the same B begins, it is equal to our AC. We'll be applying these a lot. That is why I want to do a quick recap of it. Okay. Now, you also need to take note that our position vectors we considered. That is, if you have A, B, it is the same as what? Vector B minus vector A. And then finally, talking of the magnitude of a vector. So if you have a vector V whose coordinate is x, y, Then the magnitude of v, we said, is the square root of the sum of the squares of its components. So now that we know this, let's quickly look at how we can solve resultant vectors problems. So looking at our first question here, now it says a delivery rider moves from a warehouse at point W, that is 1, 2, to a store at S, 6, 4, and then to a customer's location at point C, which is 9, 7. Find the vector movement from WS, and then from S to C, and then from W to C. I've tried my best to represent this graphically over here. Now for the graphical representation, this is my y-axis, and this here is my x-axis. The scales on the x-axis are 1 centimeter is to 2 units. So every 2 boxes on my graph is 1 centimeter. So I've made every 2 boxes for 2 units. And then on the y-axis, for every 1 centimeter, I've used 1 unit. So locating my points, I first of all have W, which is what? 1, 2. You see? So this here is my 1, 2, that is W. I've done that nicely here. And then S is 6, 4. So 6, 4. This is your S over here. And then you have C, which is the customer's location, 9, 7. And that is what we have here. Now, to find the vector movement from W to S, how are we going to do it? So I'll try my best so that we do it, we solve, and then we come to the graph and also try and see if we can get the answer straight from the graph. So as you can see, when we say from W to S, this is how we write it. Mathematically, you should be able to write that out whenever you have it in a word form. Okay. So what we want is vector WS. Now from our recap, WS is then going to be what? S minus W. You see? So the point at S and then that at W, and we find their difference. That is going to be, we know S to be 6, 4. So 6, 4 minus W, which is 1, 2. And evaluating that, we have 6 minus 1, which gives us 5. And then 4 minus 2, which would also give us a 2. So this is the vector WS, as simple as that. Okay, so the first one is solved. But then graphically, if you were also able to represent this, then using just your eye, you can tell the answer. Okay, and how do we do that? So from W to S, how many paces in terms of the x-axis do we need to move to get to S over here? You'll see that you have 1, 2, 3, 4, and 5. You see? And that is this 5 over here. Now, after getting your x paces, you are here. How many movements do we need to get to S? Remember, that of the y-axis is for every 2 centimeter. For every 1 centimeter is about 1 unit. So this is 1, and then this is 2. And that is the 2 over here. You see? So you can solve it this way, and you can also solve it this way as well. Let's look at the second one, that is from S to C. Now, for S to C, what we are going to do this time around is to try it first on the graph so that we see if we'll be getting the expected answer. This is S, and then this is C. So on the x-axis, we are moving 1, 2, 3. You see? So we have 3. Then on the y-axis, we are moving 1, 2, 3. So 3, 3. Now let's come and solve it and see if we are going to get the same answer. So S to C is simply what? C minus S. You see, and we know C being what? 9, 7, then minus your S, which is 6, 4. So you have 9 minus 6, which gives us a 3. And then 7 minus 4, which also gives us a 3. And as you can see, it is the same as what we have over here. You see. Now the last one, that is WS. So WC. It's simply what? C minus W. You see. Or using resultant vector, our WC, that is the resultant of all this movement, would be what? W to S. So that is W to S plus S to C. S to C. You see, then with that, we are looking for the resultant, taking S out. You see, so if we want to solve it using this method here, then our WS, which we already solved here, was 5, 2, plus SC, which was 3, 3. Hence, if we want to add or to get our WC, then we have 5 plus 3, which is an 8. Then the 2 plus 3, which is also a 5. So this here is our WC, and we are done with that. You see, and that is correct. But if you want to say, oh, maybe you had your coordinate for W and you had the coordinate of, what do you call it, C, and then you wanted to do it directly, that is also fine. Let's try that and let's see. So what we have here is what? Our WC, which, as I said initially, is a C minus W. Your C point C is what? 9, 7. So 9, 7 minus your W, which is 1, 2. So evaluating this, we have 9 minus 1, which is 8. Then 7 minus 2, which is also 5. You see, this one also gives us the answer. Now, if you want also, provided you had drawn it, you could have also checked on the graph. Now, on the x-axis, I have projected this up here. And if I want to move to C from the x coordinate of W, I'm just going to move 1, 2, 3, 4, 5, 6, 7, 8. And that is our 8 over here. Then on the y-axis, if I want to move to get to where the C's y is, taking note of my scale, I'm going to move 1, 2, 3, 4, 5 units. And that is what we have over here. You see, so that is it. In view of that, if you were to find the magnitude of WC, that is, we want the magnitude of this vector over here, then it's going to be the square root of its x component, the square root of the sum of its component. You see, and its x component was 8, so we have 8 squared plus y squared, which is 5. You see, and evaluating this, we have 8 times 8, which then gives us then a 64, then plus 5 squared, which is 25. And if you have to add these, we have the square root of 6. You have the square root of 89 as the magnitude of WC. There are so many examples we can solve under this, but because of time, I'll just end it here. And then in our subsequent videos, we'll just solve more examples. But this is just an introduction to give you a whole idea of what resultant vectors are. So all we are saying is, if you want the resultant of two vectors, you see, that is using the triangle here. If I want to move from A to C, then all I need to do is to move from A to B, then from B to C. And that is what this formula here is about. Okay. Same applies to this parallelogram as well. But before you can be able to solve this, you needed a pre-knowledge of certain concepts. That is, first of all, how to add vectors, the position vector, and then the magnitude of a vector, and then the vector between 2 points. Okay, so that will be it for this session. But then, as usual, I'll leave you with some exercises so you try on your own just to test your understanding. So these are 3 questions. No, there are 5 questions we have over here. Very, very basic ones. You can try to just test your understanding. This is How Beyond Numbers, where we learn maths the easy way. If this is your first time and you found this video helpful, you can always choose to subscribe. That is, if you so do wish, so that anytime I release a video, you'll be notified as well. Stay safe and then have a nice day. Bye for now.